Hello there. Welcome to Ancient Air documentary podcast. Picture this for a moment. You wake up one morning and step outside to find the air so thick with volcanic ash that you can barely see your hand in front of your face. The temperature has dropped 40 degrees overnight, and in the distance you can hear the rumble of storms so massive they make today's hurricanes look like gentle breezes. Sound like science fiction? Well, this was just another Tuesday, about 250 million years ago. Tonight we're diving deep into something that will completely change how you think about extreme weather. We're talking about prehistoric climate events so intense, so absolutely mind-bending, that they make our worst natural disasters look like minor inconveniences. And here's the thing that really gets me excited about this topic. The Earth we live on today, with all its storms and heat waves and blizzards, is actually the calm, peaceful version compared to what came before us. Before we get started, take a moment to hit that like button if you're genuinely curious about how our planet used to be a complete weather nightmare, and let me know in the comments where you're watching from and what the weather is like there right now. I always find it fascinating to see how different conditions are around the world, especially when we're about to explore just how wild things used to be. Now settle in, maybe grab something warm to drink, because we're about to journey back to times when the atmosphere itself was basically trying to kill everything that moved. The story we're telling tonight isn't just about big storms or hot summers. It's about climate chaos on a scale that shaped the entire course of life on Earth. So what exactly made prehistoric weather so much more extreme than anything we experience today? The answer lies in a perfect storm of factors that created conditions unlike anything in human history. We're talking about atmospheric compositions that were completely alien, volcanic activity that lasted for millions of years, and ocean patterns that could flip the global climate like a light switch. Let's start with something that sounds almost too wild to believe, but it's backed by rock-solid geological evidence. Around 252 million years ago, during what scientists call the Permian-Triassic extinction event, the Earth experienced the most catastrophic climate disaster in its history. This wasn't just bad weather. This was the planet essentially having a complete atmospheric meltdown that wiped out 96% of all marine species and 70% of land animals. The culprit behind this climate apocalypse was a series of volcanic eruptions in what is now Siberia. But when I say volcanic eruptions, I need you to completely forget about anything you've seen in movies or documentaries about modern volcanoes. These weren't isolated mountain peaks spewing lava for a few weeks or months. This was an area the size of Europe erupting continuously for nearly 2 million years straight. Picture lava flows so massive they could have covered the entire continental United States under several feet of molten rock. The sheer volume of material ejected into the atmosphere was staggering. We're talking about enough volcanic gases and particles to fundamentally alter the chemistry of the entire planet's atmosphere. The amount of sulfur dioxide alone was equivalent to what would be released if every volcano on Earth today erupted simultaneously and kept erupting for thousands of human lifetimes. But the volcanic activity was just the beginning of the climate chaos. All that sulfur dioxide mixed with water vapor in the atmosphere to create sulfuric acid clouds that blocked sunlight and triggered what paleoclimatologists call a volcanic winter. Temperatures plummeted globally, sometimes dropping by as much as 15 degrees Celsius in just a few decades. Imagine winter conditions lasting for centuries across the entire planet. Then, as if the volcanic winter wasn't devastating enough, the climate swung in the opposite direction. The massive amounts of carbon dioxide released by the eruptions created a greenhouse effect so intense that global temperatures eventually soared to levels that would make today's hottest days feel comfortable. Ocean temperatures rose so high that they couldn't hold dissolved oxygen, creating vast dead zones where nothing could survive. The weather patterns during this period were unlike anything in recorded history. Storm systems, fed by the extreme temperature differences between regions, became absolutely monstrous. We have geological evidence of rainfall so intense it carved canyons in solid rock, within just a few thousand years. Wind patterns were so chaotic that they redistributed entire deserts' worth of sand and dust across continents. What makes this period even more fascinating from a scientific perspective is how we know about these extreme conditions. Paleoclimatologists have developed incredible techniques for reading the Earth's ancient climate records. They analyze ice cores, sediment layers, fossilized tree rings, and even the chemical composition of ancient soils to reconstruct what the weather was like millions of years ago. One of the most revealing pieces of evidence comes from studying the ratios of different oxygen isotopes in ancient rocks and fossils. These isotope signatures act like prehistoric thermometers, telling us exactly how hot or cold the oceans and atmosphere were at different points in time. When scientists first started analyzing samples from the Permian-Triassic boundary, they couldn't believe the readings. The temperature swings were so extreme they initially thought their instruments were malfunctioning. But it wasn't just the Permian period that experienced climate chaos. Throughout Earth's prehistory, the planet went through cycles of extreme weather that make our current climate look remarkably stable. During the Cretaceous period, about 100 million years ago, the planet was so warm that palm trees grew at the North Pole, and there was no ice anywhere on Earth. Ocean temperatures near the equator reached levels that would be instantly fatal to most marine life today. The atmospheric composition during the Cretaceous was radically different from today. Carbon dioxide levels were sometimes 5 times higher than current concentrations, creating a greenhouse effect so powerful that seasonal temperature variations were minimal even at the poles. But this wasn't just a case of everything being uniformly hot. The extreme greenhouse conditions created weather patterns that were both more intense and more unpredictable than anything we see today. Tropical storm systems during the Cretaceous were absolutely massive, with some paleoclimatic models suggesting hurricanes that could maintain their strength across entire ocean basins. These weren't the relatively small, short-lived storms we're familiar with today. We're talking about weather systems the size of continents that could persist for months at a time. The monsoon patterns during this period were equally extreme. Seasonal rainfall in some regions was so intense that it created temporary inland seas covering thousands of square miles. The geological record shows evidence of flash floods so powerful they moved boulders the size of houses across hundreds of miles of terrain. What's particularly striking about Cretaceous weather is how quickly it could change. The high atmospheric carbon dioxide levels made the climate system extremely sensitive to small changes in solar radiation or volcanic activity. A relatively minor volcanic eruption could trigger temperature swings of 10 degrees or more within just a few decades, causing dramatic shifts in precipitation patterns and storm intensity. The ocean currents during the Cretaceous were also completely different from today's patterns. Without polar ice caps to drive the deep ocean circulation we're familiar with, warm tropical waters circulated all the way to the poles. This created a climate system where heat distribution was much more even globally, but also much more unstable. Small changes in ocean temperature could rapidly cascade into major climate shifts affecting the entire planet. Perhaps most fascinating of all is how life managed to survive and even thrive during these periods of extreme weather. The fossil record shows that while many species went extinct during the most severe climate events, others evolved remarkable adaptations to cope with the chaotic conditions. Some plant species developed the ability to rapidly adjust their metabolism based on atmospheric carbon dioxide levels, while certain marine organisms evolved shells that could withstand the acidic conditions created by volcanic emissions. The dinosaurs themselves were products of this extreme climate variability. Their evolution was shaped by millions of years of dramatic weather swings that favored large, adaptable species capable of surviving in rapidly changing environments. The same climate chaos that made their world so dangerous also created the evolutionary pressures that led to some of the most successful large animals in Earth's history. But the prehistoric climate extremes weren't limited to just the distant past. Even relatively recent periods in Earth's history experienced weather patterns far more intense than anything in human experience. During the Paleocene-Eocene thermal maximum, about 56 million years ago, global temperatures rose by at least 8 degrees Celsius in just 20,000 years. While that might sound gradual, it represents one of the most rapid climate changes in the geological record. The weather during this thermal maximum was characterized by extreme seasonal variations and unprecedented storm intensity. Paleoclimatic evidence suggests that some regions experience temperature swings of over 40 degrees Celsius between seasons, while tropical storms regularly reached intensities that would be categorized as beyond anything on our current hurricane scales. What makes studying these ancient climate extremes so important isn't just scientific curiosity. Understanding how the Earth's climate system behaved under different atmospheric conditions gives us crucial insights into how complex climate systems respond to rapid changes. The geological record provides us with natural experiments on a scale impossible to replicate in laboratories, showing us what happens when atmospheric chemistry, ocean circulation, and weather patterns are pushed to their absolute limits. The techniques scientists use to study these prehistoric weather patterns continue to reveal new details about just how extreme conditions could become. Recent advances in analyzing microscopic fossils have allowed researchers to reconstruct seasonal weather patterns from millions of years ago with remarkable precision. These studies consistently show that prehistoric weather wasn't just more extreme in terms of average conditions, but also much more variable and unpredictable from year to year. As we continue exploring the fascinating world of prehistoric climate extremes, we'll discover how ice ages created weather patterns that make today's polar vortex events look mild, and how the breakup of ancient supercontinents triggered atmospheric changes so dramatic they reshaped the entire planet's weather systems. The story of Earth's climate history is far from over, and each new discovery reveals just how wild our planet's weather has been throughout its incredible 4.5 billion year journey. The ice ages represent some of the most dramatic examples of prehistoric weather extremes, and they were far more complex and violent than most people realize. When we think of ice ages today, we might picture a gradual cooling that slowly brought glaciers south. But the reality was a chaotic dance of rapid climate shifts that could plunge the planet into deep freeze or snap it back to warm conditions within just a few human generations. During the last glacial maximum, about 20,000 years ago, massive ice sheets covered nearly a third of all land surfaces. But here's what makes this truly mind-blowing. These weren't just bigger versions of today's ice caps. We're talking about ice formations over 2 miles thick, stretching from the Arctic Ocean all the way down to what is now New York City. The weight of these glaciers was so immense that they actually pressed the Earth's crust downward by hundreds of feet. The weather patterns created by these continental ice sheets were absolutely brutal. The boundary between the frozen wasteland and the unfrozen world created some of the most intense storm systems in Earth's history. Temperature gradients of 60 degrees Celsius or more existed within just a few hundred miles, creating atmospheric conditions that generated winds strong enough to sandblast rock formations. What's particularly fascinating is how quickly these ice age conditions could change. Scientists studying ice cores from Greenland have discovered evidence of temperature swings of 15 degrees Celsius happening in less than a decade. Imagine the entire climate of your region completely transforming within your lifetime, not gradually, but in sudden, violent lurches that would make adaptation nearly impossible. The dust storms during glacial periods were on a scale that defies imagination. With so much of the world's water locked up in ice, vast areas that are now fertile land became barren dust bowls. Wind patterns supercharged by the extreme temperature differences between ice sheets and unfrozen regions created dust storms that could carry material across entire continents. Sediment cores from the ocean floor show layers of dust so thick they represent single storm events that dumped millions of tons of particles into the atmosphere. These dust clouds weren't just inconvenient, they fundamentally altered global weather patterns by changing how much solar radiation reached the Earth's surface. Some regions experienced decades of perpetual twilight as dust and ice crystals in the atmosphere scattered and absorbed incoming sunlight. The feedback loops created by these conditions could rapidly accelerate cooling trends, pushing the planet even deeper into glacial conditions. But perhaps the most terrifying aspect of Ice Age weather was what happened when the glaciers started to melt. The transition periods between glacial and interglacial conditions were characterized by climate chaos that makes our current concerns about sea level rise seem modest. As massive ice sheets collapsed, they released enormous volumes of fresh water into the oceans, disrupting ocean circulation patterns that had remained stable for thousands of years. The most dramatic example of this occurred during what scientists call the Younger Dryas period, about 12,000 years ago. Just as the last ice age was ending and global temperatures were warming, a massive pulse of glacial meltwater suddenly shut down the Atlantic Ocean's circulation system. Within just a few years, temperatures across the North Atlantic region plummeted back to near glacial conditions, creating a 1,000-year-long cold snap that came out of nowhere. The weather during the Younger Dryas was characterized by extreme instability. Storm tracks shifted dramatically as ocean currents reorganized themselves. Regions that had been experiencing gradual warming suddenly found themselves dealing with blizzards and ice storms that lasted for months. The rapid climate shifts created conditions where different seasons could vary by 40 degrees from their previous patterns, making it nearly impossible for plant and animal communities to adapt. Moving even further back in time, we encounter the snowball Earth events, periods when the entire planet was covered in ice from the poles to the equator. These episodes, which occurred several times between about 800 and 600 million years ago, represent the most extreme weather conditions Earth has ever experienced. During snowball Earth periods, average global temperatures dropped to -50 degrees Celsius. The oceans froze solid to depths of over a kilometre in some regions. The only liquid water on the planet existed in small pockets near volcanic vents, or in underground systems heated by geothermal activity. The weather during these periods was dominated by massive ice storms and blizzards driven by the minimal heat energy available from geothermal sources and the faint sunlight that managed to penetrate the ice-covered atmosphere. What makes snowball Earth events even more remarkable is how they ended. The same volcanic activity that contributed to the initial cooling eventually built up enough carbon dioxide in the atmosphere to create an extreme greenhouse effect. When the ice finally started to melt, it happened catastrophically fast. Global temperatures rose by as much as 50 degrees Celsius in just a few thousand years, creating weather conditions so intense that the geological record shows evidence of hypercanes, hurricane-like storms with wind speeds exceeding 300 miles per hour. The transition out of snowball Earth conditions created some of the most violent weather in the planet's history. As the ice melted, massive amounts of fresh water flooded into the oceans, creating density differences that drove ocean currents at speeds far exceeding anything seen today. These turbulent ocean conditions, combined with the extreme atmospheric instability created by rapid warming, generated storm systems of unprecedented intensity. Continental drift also played a crucial role in creating prehistoric weather extremes. When all the continents were joined together in the supercontinent Pangaea, about 300 million years ago, the interior regions experienced some of the most severe continental climate conditions ever recorded. Without moderating ocean influences, seasonal temperature swings in central Pangaea reached extremes of over 70 degrees Celsius between summer and winter. The monsoon systems that developed around Pangaea were absolutely massive. During summer months, the heating of the vast continental interior created low-pressure systems so intense they drew moisture from oceans thousands of miles away. The resulting monsoons brought rainfall measured not in inches per hour, but in feet per day. Flash floods carved out canyon systems in just a few seasons that would take modern rivers millions of years to create. But it was the seasonal wind patterns around Pangaea that created some of the most extreme weather conditions. During winter months, cold air masses building up over the continental interior would eventually break free in massive outflow events. These weren't just cold snaps. They were continental-scale avalanches of frigid air that could drop temperatures by 30 degrees Celsius in a matter of hours across areas the size of modern-day Asia. The dust storms generated by these extreme wind patterns were visible from space, if there had been anyone in space to see them. Paleoclimatic evidence shows that single storm events moved enough sediment to bury entire mountain ranges under hundreds of feet of dust and sand. The atmospheric loading from these dust storms was so intense it created its own weather patterns, generating electrical storms with lightning strikes, powerful enough to fuse sand into glass across vast areas. Ocean chemistry during these prehistoric periods also contributed to extreme weather patterns in ways we're only beginning to understand. During periods of high atmospheric carbon dioxide, the oceans became significantly more acidic, which affected evaporation rates and storm formation. Acidic oceans evaporate differently than modern seawater, creating atmospheric moisture patterns that fed into storm systems with characteristics unlike anything we observe today. The geological evidence for these extreme weather patterns comes from some truly remarkable sources. Scientists have found fossilized raindrop impressions in ancient sediments that reveal precipitation so intense it created craters in soft ground. Storm deposits show evidence of hailstones the size of bowling balls, preserved in sedimentary layers that demonstrate just how violent these ancient weather systems could become. Tree ring data from petrified forests reveals growing seasons so chaotic that some trees show evidence of multiple false starts in a single year, as extreme weather events repeatedly disrupted normal growth patterns. These ancient trees lived through climate conditions so variable that their growth rings look more like abstract art than the regular patterns we see in modern specimens. Perhaps, most remarkably, some fossilized animal burrows show evidence of creatures that spent their entire lives underground, apparently adapting to surface weather conditions too extreme to survive in. These weren't small creatures hiding from predators, but large animals that evolved elaborate tunnel systems to escape atmospheric conditions that were simply too harsh for surface living. The atmospheric pressure during some of these prehistoric periods was also dramatically different from today. During the Carboniferous period, atmospheric oxygen levels reached 35% compared to today's 21%. This created weather conditions unlike anything in human experience, with lightning strikes so intense they could start fires in solid rock, and storm systems that generated electrical activity powerful enough to create their own magnetic fields. These high oxygen conditions also allowed for fires of incredible intensity. Forest fires during the Carboniferous weren't just bigger than modern wildfires, they were fundamentally different phenomena. With so much oxygen available, fires could burn through solid rock and continue underground for decades. The smoke and ash from these fires created their own weather patterns, generating fire tornadoes and ash storms that could persist for years after the original fire had burned out. The volcanic activity during the Carboniferous period created weather patterns that seem almost impossible to believe. These weren't just larger versions of modern volcanic eruptions. We're talking about volcanic systems that operated on continental scales, with lava tubes stretching for thousands of miles underground and surface eruptions that could maintain themselves for centuries at a time. The ash clouds from these massive eruptions created their own unique weather phenomena. Unlike modern volcanic ash that disperses relatively quickly, the high oxygen atmosphere allowed volcanic particles to remain suspended for decades. These persistent ash clouds acted like atmospheric sandpaper, creating friction that generated electrical storms, unlike anything we see today. Lightning strikes during these periods were so frequent and intense that some regions experienced nearly continuous electrical activity for months at a time. But perhaps the most alien aspect of Carboniferous weather was how the extreme atmospheric conditions affected precipitation patterns. The combination of high oxygen levels and volcanic ash created rain that was significantly more corrosive than modern precipitation. This acidic rainfall could dissolve limestone formations within just a few decades, carving out cave systems and underground rivers at rates that would be impossible under current atmospheric conditions. The wind patterns during this period were equally extraordinary. The higher atmospheric density created by increased oxygen levels meant that wind systems could carry much more energy than modern weather patterns. Storm fronts moved with such force that they could literally sandblast entire mountainsides smooth within a single season. Paleoclimatic evidence shows wind-carved rock formations that could only have been created by sustained winds exceeding 200 miles per hour. Moving forward in time, the Jurassic period presents us with yet another example of how prehistoric weather could reach extremes that dwarf modern conditions. During the height of the Jurassic, about 170 million years ago, the planet experienced what scientists call hyper-greenhouse conditions. Global temperatures were so elevated that thermal gradients between the equator and poles were minimal, creating weather patterns that operated on completely different principles than today's climate system. Without the strong temperature gradients that drive modern weather systems, Jurassic storms were powered by different mechanisms entirely. Instead of the familiar pattern of high and low pressure systems we know today, weather during this period was dominated by convective systems that could maintain themselves for weeks at a time. These massive thunderstorm complexes would form over the superheated oceans and slowly drift across continents, dumping rainfall measured in feet rather than inches. The fossil record from this period reveals evidence of plant communities that were specifically adapted to these extreme precipitation patterns. Some fossilized tree species show root systems that extended over 100 feet deep, apparently evolved to survive the alternating periods of massive flooding and extended drought that characterized Jurassic weather patterns. The ocean temperatures during the Jurassic created their own unique atmospheric phenomena, with surface water temperatures reaching levels that would be lethal to most modern marine life. Evaporation rates were so high that atmospheric moisture content sometimes exceeded 50%. This created a greenhouse effect so intense that nighttime temperatures often remained within just a few degrees of daytime highs, even in polar regions. These extreme moisture levels generated weather systems that were essentially permanent hurricanes covering vast areas of the ocean. Unlike modern hurricanes that derive their energy from temperature differences between air masses, Jurassic hypercanes were powered purely by the massive amounts of water vapor available in the atmosphere. Storm systems could maintain hurricane-force winds for months at a time, creating ocean waves that regularly exceeded heights of 300 feet. The transition between the Jurassic and Cretaceous periods marked another dramatic shift in global weather patterns. As atmospheric carbon dioxide levels continued to rise, the planet's climate system became increasingly unstable. Small changes in solar radiation or volcanic activity could trigger massive shifts in weather patterns that would persist for thousands of years. During the early Cretaceous, paleoclimatologists have identified evidence of what they call climate flickering, where global weather patterns would rapidly switch between different stable states. A region that experienced tropical conditions for centuries could suddenly shift to temperate or even Arctic conditions within just a few decades, then switch back just as quickly. These rapid climate transitions created evolutionary pressures unlike anything in Earth's history. Species that couldn't rapidly adapt to changing conditions faced extinction, while those that developed flexible survival strategies thrived. The dinosaurs that dominated this period were essentially products of this climate chaos, evolved to survive in a world where the weather could change dramatically within a single generation. The marine environments during the Cretaceous were equally extreme. Ocean temperatures in tropical regions sometimes exceeded 40 degrees Celsius, hot enough to kill most modern fish species instantly. These superheated oceans created their own weather patterns, with massive evaporation events that could lift billions of tons of water into the atmosphere within just a few hours. The resulting precipitation events were absolutely catastrophic. Paleoclimatic evidence shows flood deposits from this period, that indicate rainfall rates exceeding 20 inches per hour sustained for weeks at a time. These weren't just heavy rains. They were atmospheric river systems that could dump the equivalent of an entire year's modern precipitation in just a few days. Perhaps most remarkably, the Cretaceous oceans were so warm that they experienced what scientists call oceanic overturning events. The normal layering of ocean water by temperature and salinity would occasionally break down completely, causing the entire water column to mix rapidly. These events released massive amounts of dissolved gases and nutrients into the atmosphere, creating their own unique weather phenomena. The atmospheric chemistry during these oceanic overturning events was toxic by modern standards. Hydrogen sulfide and methane released from deep ocean waters created atmospheric conditions that would be immediately lethal to most current life forms. Yet the geological record shows that life not only survived these events, but often diversified rapidly in their aftermath. The end of the Cretaceous period brought perhaps the most famous example of how external factors could create extreme weather conditions. The asteroid impact that ended the age of dinosaurs didn't just create a massive explosion, it triggered a cascade of atmospheric changes that made the planet essentially uninhabitable for months or even years. The initial impact vaporized thousands of cubic miles of rock, launching debris into the atmosphere at velocities that carried material completely around the planet. This debris re-entered the atmosphere as a global firestorm, with temperatures hot enough to ignite forests on every continent simultaneously. The heat generated by this re-entry was so intense that it temporarily raised global surface temperatures to over 60 degrees Celsius. But the immediate heating was just the beginning of the climate catastrophe. The massive amounts of dust and debris launched into the upper atmosphere blocked sunlight for months, creating what scientists call impact winter. Global temperatures plummeted by as much as 20 degrees Celsius, while photosynthesis essentially stopped across the entire planet. The weather patterns during this impact winter were unlike anything else in Earth's history. With no solar heating to drive normal atmospheric circulation, weather systems were powered entirely by the residual heat stored in the oceans and the ongoing volcanic activity triggered by the impact. Storm systems became chaotic and unpredictable, with some regions experiencing simultaneous blizzards and acid rain. The recovery from impact winter conditions created yet another phase of extreme weather. As the atmospheric debris finally settled and sunlight returned to the Earth's surface, the accumulated carbon dioxide from fires and volcanic activity created an intense greenhouse effect. Global temperatures rose rapidly, often swinging from below freezing to tropical conditions within just a few years. These rapid temperature swings created atmospheric instability that generated some of the most violent storms in the geological record. The transition zones between recovering ecosystems experienced weather conditions so chaotic that they prevented normal plant succession for decades. Some regions show evidence of repeated cycles of forest growth and destruction, as extreme weather events prevented the establishment of stable ecosystems. The Paleocene period that followed the extinction event was characterized by continued climate instability. The disruption of normal ocean circulation patterns created regional weather extremes that persisted for millions of years. Some areas experienced permanent drought conditions, while others were subjected to continuous monsoon-like precipitation that prevented soil formation and ecosystem development. What makes the study of these prehistoric weather extremes so compelling is how they reveal the true potential of Earth's climate system. The relatively stable conditions we've experienced throughout human history represent just a tiny fraction of the weather patterns our planet is capable of generating. The geological record shows us a world where climate chaos was the norm rather than the exception, where weather systems operated on scales and intensities that challenge our understanding of atmospheric physics. The techniques scientists use to study these ancient weather patterns continue to evolve and reveal new details about just how extreme conditions could become. Recent advances in analyzing microscopic marine fossils have allowed researchers to reconstruct daily weather patterns from tens of millions of years ago. These studies consistently show that prehistoric weather wasn't just more extreme on average, but also far more variable and unpredictable than anything in human experience. Climate modeling based on these paleoclimatic reconstructions suggests that Earth's atmosphere has operated in fundamentally different modes throughout its history. The stable, predictable weather patterns that have characterized the last few thousand years appear to be the exception rather than the rule in the planet's long climate history. Understanding these prehistoric weather extremes provides crucial insights into how complex climate systems respond to rapid changes in atmospheric composition, ocean circulation, and solar radiation. Each new discovery reveals another layer of complexity in Earth's climate history, showing us just how wild and unpredictable our planet's weather systems can become when pushed beyond their normal operating parameters. As we continue to uncover evidence of these ancient climate catastrophes, we gain a deeper appreciation for both the resilience of life and the incredible power of Earth's atmospheric systems. The story of prehistoric weather is ultimately a story of survival and adaptation in the face of conditions so extreme they seem almost alien to our modern experience. The mass extinction events that punctuated Earth's history weren't just about species disappearing. They were about weather systems so catastrophically extreme that they fundamentally rewrote the rules of how our planet's atmosphere could behave. And nowhere is this more apparent than during the Triassic-Jurassic extinction event. About 201 million years ago, this particular extinction wasn't caused by an asteroid impact or a single volcanic eruption. Instead, it was triggered by what geologists call the Central Atlantic Magmatic Province, a series of volcanic eruptions that occurred as the supercontinent Pangaea began to split apart. But calling these volcanic eruptions understates the sheer magnitude of what happened. We're talking about lava flows that covered an area larger than the entire United States, releasing gases into the atmosphere for over 600,000 years. The weather patterns created by this prolonged volcanic activity were absolutely nightmarish. The initial phase released massive amounts of sulfur dioxide, creating acid rain so concentrated it could dissolve limestone buildings within months. Paleosol studies from this period show evidence of soil chemistry changes that indicate rainfall with pH levels comparable to battery acid. Entire ecosystems were essentially pickled by precipitation that was toxic to most forms of life. But the sulfur dioxide was just the opening act. As the eruptions continued, they began releasing enormous quantities of carbon dioxide and methane. The greenhouse effect created by these gases was so intense that global temperatures rose by at least 4 degrees Celsius, and possibly as much as 7 degrees, within just 20,000 years. To put that in perspective, that's roughly equivalent to experiencing the entire warming predicted for the next century, happening in what amounts to a geological instant. The ocean chemistry during this period underwent changes so dramatic they're almost impossible to comprehend. The combination of increased temperatures and volcanic emissions created conditions where large areas of the ocean became completely anoxic, meaning they contained no dissolved oxygen whatsoever. These dead zones weren't small pockets. They covered millions of square miles and extended from the surface all the way to the ocean floor. The atmospheric conditions above these dead oceans created weather phenomena that have no modern equivalent. As hydrogen sulfide gas bubbled up from the oxygen-free water, it reacted with moisture in the atmosphere to create clouds of sulfuric acid that could persist for weeks. These acid clouds didn't just produce corrosive rainfall. They also absorbed and scattered sunlight in ways that created perpetual twilight conditions across vast regions. The wind patterns during this extinction event were driven by temperature gradients so extreme they generated atmospheric circulation patterns unlike anything we see today. The superheated equatorial regions created massive convection cells that could lift air masses to altitudes of over 20 miles, well into what we now call the stratosphere. These elevated air masses would then travel toward the poles at high altitude before descending in massive downdrafts that could create surface winds exceeding 150 miles per hour. Marine sediment cores from this period reveal evidence of storm deposits that indicate individual weather events of staggering intensity. Some layers show debris that could only have been transported by tsunami-like waves generated not by earthquakes, but by atmospheric disturbances so powerful they literally moved ocean water through wind stress alone. These weren't just big waves, they were atmospheric events that temporarily reorganized entire ocean basins. The transition into the Jurassic period marked yet another phase of extreme weather instability. As volcanic activity from the Central Atlantic magmatic province finally began to wane, the planet's climate system started to reorganize itself around the new atmospheric chemistry. But this wasn't a gradual return to normal conditions. Instead, it was a series of rapid climate oscillations that created decades-long periods of weather chaos. During the early Jurassic, paleoclimatic records show evidence of what scientists call megadroughts, periods of extreme aridity that lasted for centuries at a time. These weren't just dry spells. They were atmospheric conditions so arid that humidity levels dropped below 5% across entire continents. The geological record shows evidence of dust storms during this period that moved sediment across distances of over 2,000 miles, creating dune fields in regions that are now temperate forests. But perhaps even more remarkable were the precipitation events that punctuated these drought periods. When atmospheric conditions finally shifted to allow moisture to return, the resulting rainfall was so intense it created what geologists call catastrophic flooding events. Sediment analysis shows evidence of flash floods that carved out river valleys hundreds of feet deep within just a few decades, moving boulders the size of houses across hundreds of miles of terrain. The plant communities that survived these extreme Jurassic conditions developed some of the most remarkable adaptations in the fossil record. Some species evolved the ability to completely shut down their metabolism for years at a time, essentially going dormant until favorable weather conditions returned. Others developed root systems that could extend over 200 feet deep, apparently adapted to accessing groundwater during the prolonged drought periods. Moving forward to the Cretaceous period, we encounter weather patterns that were extreme in completely different ways. The breakup of Pangaea had progressed to the point where ocean circulation patterns began to resemble modern configurations, but with one crucial difference. Without polar ice caps, the temperature gradients between equator and poles were much smaller than today, creating atmospheric circulation patterns that operated on entirely different principles. The Cretaceous greenhouse climate created what paleoclimatologists call equable conditions, where seasonal temperature variations were minimal even at high latitudes. But don't mistake equable for calm. The high atmospheric carbon dioxide levels, sometimes reaching concentrations over 4 times higher than today, created weather systems of unprecedented intensity powered by the massive amounts of energy available in the superheated atmosphere. Storm systems during the Cretaceous regularly reached sizes that covered entire ocean basins. Unlike modern hurricanes that derive their energy from temperature contrasts between air masses, Cretaceous hypercanes were powered by the sheer amount of water vapor available in the atmosphere. These weren't temporary weather events. Some storm systems appear to have maintained themselves for months at a time, creating persistent areas of extreme weather that migrated slowly across the planet's surface. The ocean temperatures during peak Cretaceous conditions reached levels that seem almost impossible. Paleothermometry studies of marine fossils indicate surface water temperatures in tropical regions sometimes exceeded 37 degrees Celsius, while even polar oceans maintained temperatures above 20 degrees. These superheated oceans created evaporation rates so high that atmospheric humidity levels regularly exceeded 60%, creating greenhouse conditions so intense that nighttime temperatures often remained within just a few degrees of daytime highs. The hypergreenhouse conditions of the mid-Cretaceous created precipitation patterns that were both more intense and more erratic than anything in the modern world. Paleosol studies reveal evidence of individual rainfall events that deposited over 10 feet of water within a few days, followed by drought periods that could last for decades. The alternation between these extreme wet and dry phases created erosion patterns that carved out entire mountain ranges within just a few million years. But it was the atmospheric chemistry during the Cretaceous that created some of the most alien weather conditions in Earth's history. The combination of high carbon dioxide levels and elevated ocean temperatures created atmospheric conditions where water vapor made up over 10% of the total atmosphere in some regions. This created weather phenomena that have no modern analogues, including precipitation events where pure water vapor would condense directly out of the atmosphere without the formation of traditional clouds. The lightning activity during these high humidity periods was absolutely extraordinary. The combination of elevated atmospheric moisture and the electrical charge generated by rapid convection created electrical storms of unprecedented intensity. Paleomagnetic studies of rocks from this period show evidence of lightning strikes so powerful they created their own magnetic anomalies, indicating electrical discharges that far exceeded anything measured in modern storms. The wind patterns during the Cretaceous were equally extreme. The minimal temperature gradients between different latitudes meant that atmospheric circulation was driven primarily by convection, rather than the pressure gradients that dominate modern weather systems. This created wind patterns that were both less predictable and more intense than contemporary weather, with some paleoclimatic models suggesting sustained wind speeds that regularly exceeded 100 miles per hour across vast areas. The transition between the Cretaceous and Paleogene periods brought perhaps the most dramatic example of how external events could trigger cascading climate changes. The Chicxulub impact that ended the age of dinosaurs created weather conditions so extreme, they essentially reset the planet's entire atmospheric system within just a few years. The immediate aftermath of the impact created what scientists call a global firestorm. The debris ejected by the impact re-entered the atmosphere at such high velocities that it heated the air to temperatures exceeding 1600 degrees Celsius. This superheated atmosphere ignited forests across every continent simultaneously, creating fires so intense they could burn through solid rock formations. The smoke and ash from these global wildfires combined with the impact debris to create atmospheric conditions unlike anything else in Earth's history. Sunlight was reduced to less than 1% of normal levels for over 6 months, while temperatures plummeted by as much as 28 degrees Celsius. But this wasn't just a simple cooling event. The combination of impact debris, volcanic ash, and smoke particles created atmospheric chemistry that generated acid rain with pH levels below 2, making it more corrosive than stomach acid. The weather patterns during this impact winter were powered entirely by the thermal energy stored in the oceans and the ongoing tectonic activity triggered by the impact. Without solar heating to drive normal atmospheric circulation, storm systems became chaotic and unpredictable. Some regions experienced simultaneous snow and acid rain, while others dealt with dust storms generated by the complete absence of vegetation to hold soil in place. The recovery from impact winter conditions created yet another phase of extreme weather as the atmospheric debris finally cleared and sunlight returned to Earth's surface. The accumulated carbon dioxide from the global fires and impact-triggered volcanism created an intense greenhouse effect that caused global temperatures to rise by over 10 degrees Celsius within just a few thousand years. This rapid warming created atmospheric instability that generated some of the most violent weather systems in the geological record. The transition from frozen wasteland to greenhouse conditions happened so quickly that atmospheric circulation patterns couldn't establish stable configurations. Weather systems during this recovery period were characterized by extreme unpredictability, with some regions experiencing tornado-like conditions that persisted for months at a time. The Paleocene period that followed was marked by continued climate instability as Earth's atmospheric system struggled to reach a new equilibrium. Ocean circulation patterns disrupted by the impact event took millions of years to re-establish themselves, creating regional weather extremes that persisted long after global temperatures had stabilized. During the Paleocene-Eocene thermal maximum, about 56 million years ago, we see perhaps the most rapid natural climate change event in the geological record. Global temperatures rose by at least 8 degrees Celsius in less than 20,000 years, triggered by massive releases of carbon from ocean sediments and permafrost regions. The weather during this thermal maximum was characterized by extreme seasonal variations and storm intensities that exceeded anything in the previous climate record. The atmospheric conditions during the thermal maximum created precipitation patterns that were both more intense and more erratic than even the extreme Cretaceous conditions. Some regions experienced rainfall rates exceeding 15 inches per hour, sustained for weeks at a time, while others dealt with drought conditions so severe they prevented soil formation for thousands of years. The storm systems during this period were powered by unprecedented amounts of atmospheric energy. The rapid warming created temperature gradients so steep they generated wind shear conditions that could tear apart mountain ranges through purely atmospheric erosion. Paleoclimatic evidence shows wind-carved rock formations from this period that could only have been created by sustained winds exceeding 250 miles per hour. What makes the study of these prehistoric weather extremes so crucial is how they reveal the true potential instability of Earth's climate system. The relatively calm conditions we've experienced throughout human history represent just a tiny fraction of the weather patterns our planet is capable of generating. Every new paleoclimatic discovery reveals another layer of complexity in how atmospheric systems can respond to changing conditions. The techniques scientists use to reconstruct these ancient weather patterns continue to evolve, providing ever more detailed pictures of just how extreme prehistoric conditions could become. Isotope analysis of fossil shells now allows researchers to determine seasonal temperature variations from millions of years ago, with precision measured in degrees. These studies consistently show that prehistoric weather was not just more extreme on average, but also far more variable from season to season and year to year. Recent advances in studying microscopic marine organisms have revealed evidence of weather patterns that operated on completely different timescales than modern systems. Some storm tracks appear to have persisted for decades, creating permanent weather features that slowly migrated across ocean basins. These weren't just long-lasting storms, they were atmospheric configurations that represented entirely different modes of how Earth's weather systems could organize themselves. The implications of these discoveries extend far beyond academic curiosity. Understanding how Earth's climate system has behaved under different atmospheric conditions provides crucial insights into the fundamental physics of how weather systems respond to changing energy inputs. The prehistoric climate record serves as a natural laboratory for studying atmospheric dynamics under conditions impossible to replicate in modern experiments. Each new piece of evidence from the geological record reveals another aspect of just how wild and unpredictable Earth's weather systems have been throughout the planet's history. From the volcanic winters that could plunge global temperatures by dozens of degrees within decades, to the hyper-greenhouse conditions that created storm systems covering entire continents. Our planet's atmospheric history reads like a catalogue of meteorological extremes. The story of prehistoric weather is ultimately a testament to both the incredible power of Earth's atmospheric systems and the remarkable resilience of life itself. Despite facing weather conditions that seem almost alien to our modern experience, life not only survived these extreme climate events, but often evolved and diversified in their aftermath, creating the rich biological heritage we see around us today. As we continue to uncover new evidence of these ancient climate extremes, we gain a deeper appreciation for the complex dance between atmosphere, oceans, and life that has shaped our planet for billions of years. The prehistoric weather patterns we've explored tonight represent just a glimpse into the incredible story of how Earth's climate system has evolved and responded to changing conditions throughout the planet's long and tumultuous history. The most remarkable aspect of these prehistoric climate catastrophes is how they fundamentally changed the rules of atmospheric physics. During the late Devonian extinction event, around 375 million years ago, we see evidence of weather patterns so bizarre, they challenge our basic understanding of how atmospheres are supposed to work. This wasn't just another period of extreme temperatures or violent storms. This was a time when the very chemistry of the atmosphere created conditions that seem almost supernatural in their intensity. The late Devonian crisis was triggered by the rapid expansion of land plants across the continents. Now you might think that more plants would create better, more stable weather conditions. But the reality was exactly the opposite. These early forests were so successful at pulling carbon dioxide out of the atmosphere that they triggered a runaway cooling effect, unlike anything we see in nature today. Within just a few 100,000 years, atmospheric carbon dioxide levels dropped by over 70%, creating what scientists call biological climate forcing. But here's where it gets truly mind-bending. The massive reduction in atmospheric carbon dioxide didn't just cool the planet gradually, it created a feedback loop that generated some of the most chaotic weather patterns in Earth's history. As temperatures dropped, more water froze into ice sheets, which reflected more sunlight back to space, which caused even more cooling. The result was climate oscillations so rapid and extreme that ecosystems couldn't adapt fast enough to survive. The geological evidence for these climate oscillations is preserved in sediment cores that read like a meteorological horror story. Temperature proxies show swings of over 20 degrees Celsius happening within just a few thousand years. But these weren't smooth transitions. The climate system was essentially having a breakdown, flickering between different stable states like a broken light switch. Some regions would experience tropical conditions for decades, then suddenly shift to near-Arctic temperatures within a single generation. The storm systems during these rapid climate transitions were powered by energy gradients that dwarf anything in the modern world. When warm air masses from stable tropical regions encountered the rapidly expanding ice sheets, they created atmospheric boundaries so sharp they generated weather phenomena that have no contemporary equivalent. Paleoclimatic models suggest storm fronts with pressure gradients steep enough to create winds that could literally lift boulders off the ground and carry them for hundreds of miles. The precipitation patterns during the late Devonian were equally extreme. The rapid climate oscillations created atmospheric conditions where moisture distribution became completely chaotic. Some regions experienced what geologists call precipitation bombs, individual storm events that could dump the equivalent of several years' worth of modern rainfall within just a few days. The erosion caused by these massive precipitation events carved out river systems that still influence continental drainage patterns today. But perhaps most remarkably, the atmospheric chemistry during this period created weather conditions that were toxic in ways we're only beginning to understand. The combination of reduced carbon dioxide levels and increased oxygen from the expanding forests created atmospheric ratios that made lightning strikes far more frequent and intense than anything we see today. Some regions experienced nearly continuous electrical activity for months at a time, with lightning strikes powerful enough to fuse sand into glass formations that are still visible in the geological record. The marine environments during the late Devonian extinction reveal evidence of ocean-atmosphere interactions that operated on completely different principles than modern systems. The cooling climate created density differences in seawater so extreme that ocean circulation patterns became unstable. Instead of the relatively steady currents we're familiar with today, the late Devonian oceans experienced what oceanographers call thermohaline catastrophes, where entire ocean basins would suddenly flip their circulation patterns within just a few decades. These rapid changes in ocean circulation created weather patterns on the continents that were both unpredictable and incredibly violent. Coastal regions that had experienced stable maritime climates for millions of years suddenly found themselves dealing with continental weather extremes as ocean currents that had moderated their temperatures simply disappeared. The fossil record shows evidence of marine organisms that had thrived in warm coastal waters suddenly buried under sediments deposited by massive continental ice sheets that formed within just a few centuries. Moving forward to the Carboniferous period, we encounter a completely different type of weather extreme. The atmospheric oxygen levels during this time reached concentrations that created fire behavior unlike anything in the modern world. With oxygen levels at 35% of the atmosphere, compared to today's 21%, wildfires could burn with intensities that seem almost impossible to believe. These weren't just bigger forest fires. The high oxygen concentrations created combustion conditions so intense that fires could burn through solid rock formations and continue underground for decades. Paleobotanical evidence shows charcoal deposits from this period that indicate flame temperatures exceeding 2,000 degrees Celsius, hot enough to melt copper. Some fire events were so intense they created their own weather systems, generating fire tornadoes that could maintain themselves for weeks at a time. The atmospheric pressure during the Carboniferous was also significantly different from today, creating weather dynamics that operated according to different physical principles. The higher density atmosphere meant that wind systems could carry much more kinetic energy than modern weather patterns. Storm fronts moved with such force that they could literally reshape mountain ranges through purely atmospheric erosion. Geological evidence shows wind-carved rock formations that could only have been created by sustained winds exceeding 300 miles per hour. The electrical activity during Carboniferous storms was absolutely extraordinary. The combination of high atmospheric density and elevated oxygen levels created conditions where lightning strikes were not just more frequent, but fundamentally different in character. Some lightning events appear to have created sustained electrical arcs that could persist for minutes, rather than milliseconds, generating continuous plasma channels that acted like atmospheric blowtorches. The precipitation chemistry during this period was also unique. The high oxygen levels caused rainwater to have significantly different chemical properties than modern precipitation. This oxygen-rich rain was so reactive it could dissolve limestone formations within just a few decades, carving out cave systems and underground rivers at rates that would be impossible under current atmospheric conditions. But it was the interaction between the extreme fire behavior and the unusual atmospheric chemistry that created some of the most alien weather conditions in Earth's history. Massive fires burning at temperatures hot enough to vaporize rock created smoke clouds that weren't just larger than modern wildfire smoke, they were chemically different. These smoke clouds contained vaporized minerals and metals that, when they condensed back out of the atmosphere, created precipitation events where it literally rained molten metal in some regions. The Permian period brought yet another category of weather extremes as the planet's land masses consolidated into the supercontinent Pangaea. The sheer size of this continental mass created climate conditions that have no modern parallel. The interior regions of Pangaea were so far from moderating ocean influences that they experienced seasonal temperature variations exceeding 80 degrees Celsius between summer and winter. During Permian summers, the continental interior became so superheated that it created low-pressure systems of unprecedented intensity. These massive heat lows could draw moisture from oceans thousands of miles away, creating monsoon systems that covered areas larger than modern-day Asia. The resulting precipitation events were measured not in inches per year, but in feet per day during peak monsoon periods. But it was during Permian winters that the most extreme weather conditions developed. The massive continental interior would cool so rapidly that it created high-pressure systems with atmospheric pressures significantly higher than anything recorded in the modern world. When these supercooled air masses finally broke free from the continental interior, they created outflow events that were essentially atmospheric tsunamis of frigid air. These cold air outbreaks weren't just winter storms. They were continental-scale avalanches of air that could drop temperatures by 40 degrees Celsius within hours across areas covering millions of square miles. The geological record shows evidence of permafrost formation at latitudes that are now tropical, apparently created by single weather events that froze the ground solid within just a few days. The dust storms generated by these extreme Permian wind systems were visible from orbit, if there had been anyone in orbit to observe them. Sedimentological evidence shows that individual storm events moved enough material to bury entire mountain ranges under hundreds of feet of dust and sand. The atmospheric loading from these dust storms was so intense it created its own weather patterns, with dust clouds generating their own electrical activity and precipitation systems. The transition from the Permian to the Triassic periods marked the most severe climate crisis in Earth's history, with weather conditions so extreme they eliminated over 90% of all species on the planet. The Siberian Traps volcanism that triggered this extinction didn't just release lava, it created atmospheric conditions that were toxic on a planetary scale, with weather patterns that seemed designed to make the planet uninhabitable. The initial phase of the extinction was dominated by what geochemists call acid precipitation events. The massive amounts of sulfur dioxide released by the volcanic activity created rainfall so acidic it could dissolve limestone bedrock within months. Paleosol studies show evidence of soil chemistry changes that indicate precipitation with pH levels approaching 0, essentially turning rain into dilute sulfuric acid across vast areas of the planet. But the acid rain was just the beginning of the atmospheric catastrophe. As the Siberian volcanism continued, it began releasing unprecedented amounts of carbon dioxide and methane into the atmosphere. The greenhouse effect created by these gases was so intense that global temperatures rose by at least 10 degrees Celsius and possibly as much as 15 degrees within just tens of thousands of years. The ocean chemistry during this extinction event underwent changes so dramatic they created weather patterns that have no modern equivalent. Large areas of the ocean became completely anoxic and began producing hydrogen sulfide gas that bubbled up into the atmosphere. This created toxic clouds that could persist for weeks, generating precipitation that was poisonous to most forms of life. The atmospheric circulation during the end Permian extinction was driven by temperature gradients so extreme they created wind patterns unlike anything in Earth's climate history. The superheated equatorial regions generated convection cells so powerful they could lift air masses into the stratosphere, creating a form of atmospheric mixing that brought toxic gases from the upper atmosphere down to ground level across the entire planet. The recovery from the end Permian extinction took millions of years, during which the planet's weather systems remained chaotic and unpredictable. The early Triassic period was characterized by continued climate instability, with atmospheric conditions that oscillated between extremely hot greenhouse states and brief cooling periods triggered by massive dust storms and volcanic ash clouds. The weather patterns during the early Triassic recovery were dominated by what paleoclimatologists call environmental whiplash, where ecosystems would begin to recover from one extreme condition only to be hit by another completely different type of climate disaster. The fossil record shows repeated cycles of ecosystem collapse and recovery, apparently driven by weather conditions so variable that stable ecological communities couldn't establish themselves for millions of years. Perhaps most remarkably, some of the most extreme weather conditions in Earth's history occurred during periods when life was actually thriving and diversifying. The Mesozoic era, despite experiencing some of the most intense climate conditions on record, was also the time when dinosaurs evolved and dominated terrestrial ecosystems for over 160 million years. The key to understanding how life survived these prehistoric weather extremes lies in recognizing that evolution operates on timescales that allow adaptation to even the most severe climate conditions, as long as those conditions persist long enough for natural selection to operate. The dinosaurs and other Mesozoic organisms weren't just surviving extreme weather. They were products of that extreme weather, evolved specifically to thrive in climate conditions that would be instantly lethal to most modern species. The atmospheric conditions that created these extreme weather patterns also drove evolutionary innovations that have no modern parallels. Some plant species evolved the ability to rapidly adjust their metabolic rates based on atmospheric carbon dioxide levels that could change by hundreds of % within just a few decades. Others developed root systems that could extend over 300 feet deep, apparently adapted to survive the alternating flood and drought cycles that characterized many prehistoric climate periods. The study of these prehistoric weather extremes continues to reveal new details about just how far Earth's climate system can be pushed before it breaks down completely. Recent advances in paleoclimatic modeling have shown that some of the conditions we've discussed tonight were actually close to the theoretical limits of how extreme weather can become on a planet like Earth, while still maintaining liquid water at the surface. The implications of these discoveries extend far beyond understanding ancient climate. Every new piece of evidence from the geological record provides crucial insights into how complex atmospheric systems respond to rapid changes in energy inputs, chemical composition, and surface conditions. This knowledge is becoming increasingly important as we face our own period of rapid climate change, though thankfully at rates and intensities far below the prehistoric extremes we've explored. The story of prehistoric weather is ultimately a story about the incredible resilience and adaptability of both Earth's climate system and the life that has evolved within it. Despite facing weather conditions that seem almost alien to our modern experience, life not only survived these extreme climate events, but used them as opportunities for evolutionary innovation and diversification. As we continue to uncover new evidence of these ancient climate catastrophes, we gain a deeper understanding of the complex relationships between atmosphere, oceans, geology, and biology that have shaped our planet throughout its long history. Each discovery reveals another layer of the incredible story of how Earth's weather systems have evolved and adapted over billions of years of continuous change. The prehistoric weather patterns we've explored tonight represent just a fraction of the climate extremes that have occurred throughout Earth's history. Every rock formation, every fossil, every chemical signature preserved in ancient sediments tells part of this incredible story of atmospheric chaos and recovery. And while we may never experience weather conditions as extreme as those that characterize much of our planet's past, understanding these prehistoric climate events gives us a profound appreciation for both the power of natural forces and the remarkable stability of the climate conditions that have allowed human civilization to develop and thrive. The techniques scientists use to study these ancient weather patterns continue to evolve, providing ever more detailed reconstructions of climate conditions from hundreds of millions of years ago. New methods of analyzing microscopic fossils, chemical isotopes, and mineral formations are revealing weather patterns that operated on timescales from individual storm events to multi-million-year climate cycles. These advances in paleoclimatic research are not just filling in details about ancient weather. They're revealing fundamental principles about how planetary atmospheres work under extreme conditions. Knowledge that has applications ranging from understanding climate change on Earth to predicting weather patterns on planets orbiting other stars. The prehistoric weather extremes we've discussed tonight remind us that the calm, predictable climate conditions of recent human history are actually quite unusual in the context of Earth's long meteorological story. Our planet's atmosphere is capable of far more dramatic and violent behavior than anything we've experienced, and understanding these capabilities is crucial for appreciating both the fragility and the resilience of the climate system that sustains all life on Earth. As we look toward the future, the lessons learned from studying prehistoric weather extremes provide valuable insights into how climate systems respond to rapid changes and what we might expect as our own planet's atmospheric composition continues to evolve. While we're fortunately not facing anything approaching the extreme conditions that characterized much of Earth's prehistoric climate, understanding these ancient weather patterns helps us better prepare for and adapt to the climate challenges that lie ahead. The story of prehistoric weather is far from complete. Every new fossil discovery, every advance in analytical techniques, every improvement in climate modelling reveals new details about the incredible meteorological history of our planet. As we continue to explore this fascinating field, we can expect to uncover even more remarkable examples of how extreme Earth's weather systems can become when conditions push them beyond their normal operating parameters. The story becomes even more extraordinary when we examine the role that ancient supercontinents played in creating weather patterns that were fundamentally different from anything we see today. During the assembly and breakup of these massive landmasses, Earth's climate system underwent reorganization so dramatic they created entirely new categories of atmospheric behavior. When we look at the formation of Rodinia about 1 billion years ago, we're witnessing the creation of weather conditions that operated according to principles we're only beginning to understand. This supercontinent was so massive that its interior regions experienced what geologists call continental hypercontinentality, where the sheer distance from any ocean created climate conditions unlike anything in Earth's subsequent history. The seasonal temperature swings in central Rodinia exceeded 100 degrees Celsius between summer and winter. But these weren't gradual seasonal transitions like we experience today. Paleoclimatic reconstructions suggest that temperature changes of 30 degrees could occur within just a few weeks, as massive air masses built up over the continental interior and then suddenly released their stored thermal energy. During Rodinian summers, the continental interior became so superheated that it created convection cells reaching altitudes of over 30 miles into the atmosphere. These massive updrafts were powerful enough to inject water vapor and dust directly into the stratosphere, creating atmospheric mixing patterns that fundamentally altered global weather circulation. The result was precipitation events so intense they could carve out river valleys hundreds of feet deep within just a single season. But it was during Rodinian winters that the most alien weather conditions developed. The massive continental interior would radiate heat so rapidly that surface temperatures could drop below -60 degrees Celsius within just a few days. These extreme cooling events created atmospheric pressure gradients so steep they generated what paleoclimatologists call pressure wave storms, where changes in atmospheric pressure moved across the continent like shock waves, creating winds that could exceed 400 miles per hour. The dust storms generated by these pressure waves were on a scale that challenges our understanding of atmospheric physics. Sedimentological evidence shows that individual storm events could lift billions of tons of material into the atmosphere, creating dust clouds that remained suspended for months at a time. These dust clouds were so dense they could block over 90% of incoming solar radiation, creating their own weather patterns as they slowly drifted around the planet. The breakup of Rodinia, beginning around 750 million years ago, triggered a cascade of climate changes that led directly to the snowball Earth events we discussed earlier. But the transition into these global glaciation periods involved weather patterns that were even more extreme than the frozen conditions that followed. As Rodinia began to fragment, the newly formed ocean basins created atmospheric circulation patterns that were completely unstable. The interaction between the massive continental landmasses and the narrow seaways that separated them generated wind patterns that could reverse direction within just a few days, creating weather whiplash effects that prevented stable climate zones from establishing themselves. The volcanic activity associated with Rodinia's breakup created atmospheric conditions that were toxic on a global scale. Unlike the relatively localized effects of modern volcanic eruptions, the rifting process that split Rodinia apart involved volcanic systems that extended for thousands of miles along the continental margins. These weren't just individual volcanoes erupting. They were entire continental edges essentially exploding as the landmass tore itself apart. The atmospheric loading from this volcanic activity was so intense, it created weather phenomena that have no modern parallels. The combination of volcanic gases, Ash and aerosols created atmospheric chemistry that made precipitation chemically reactive in ways that transformed the very landscape it fell upon. Some regions experienced rainfall that was essentially liquid rock, as volcanic emissions condensed directly out of the atmosphere. The transition into snowball Earth conditions involved weather patterns that were paradoxically both extremely violent and eerily stable. As global temperatures began to plummet, the formation of sea ice created feedback loops that accelerated the cooling process. But this wasn't a gradual slide into glaciation. Paleoclimatic models suggest that the transition from normal conditions to global ice coverage could have occurred within just a few thousand years. During this transition period, the weather was dominated by massive ice storms that could deposit several feet of ice within just a few hours. These weren't freezing rain events like we experience today. The atmospheric conditions created ice formation processes so efficient they could turn water vapor directly into ice crystals without passing through a liquid phase, creating precipitation that was essentially solid ice falling from clear skies. The wind patterns during the transition to snowball Earth were driven by temperature gradients between the rapidly freezing oceans and the still warm continental interiors. These gradients were so extreme, they created atmospheric circulation patterns that operated like planetary-scale hurricanes, with wind speeds that regularly exceeded 200 miles per hour, and storm systems that could maintain themselves for decades at a time. Once full snowball Earth conditions were established, the weather became dominated by what glaciologists call ice sheet dynamics. The entire planet was covered by ice sheets that were sometimes over a mile thick, but these weren't static frozen wastelands. The ice sheets were constantly moving and reshaping themselves, creating weather patterns powered entirely by gravitational and geothermal energy. The storms that occurred during snowball Earth periods were unlike anything in Earth's climate history. Without liquid oceans to moderate atmospheric circulation, weather systems were powered by the minimal heat energy available from geothermal sources and the faint sunlight that managed to penetrate the ice-covered atmosphere. These storms created wind patterns that could carve channels in solid ice, generating ice flows that moved across the frozen landscape like slow-motion tsunamis. The end of snowball Earth events involved weather transitions that were even more dramatic than the initial freezing. When volcanic activity finally built up enough carbon dioxide in the atmosphere to begin melting the global ice sheets, the transition happened catastrophically fast. Global temperatures rose by as much as 60 degrees Celsius within just a few thousand years, creating weather conditions so intense they seem almost supernatural in their violence. The initial melting phase created atmospheric conditions where water existed simultaneously as ice, liquid, and vapor across the planet's surface. This created weather phenomena that have no modern equivalent, including precipitation events where it could be snowing, raining, and hailing simultaneously in the same location. The rapid phase transitions of water created atmospheric instability so extreme it generated electrical storms with continuous lightning activity that could persist for months. The massive amounts of fresh water released by the melting ice sheets created ocean circulation patterns that were completely chaotic. Instead of the relatively stable current systems we're familiar with today, the post-snowball oceans experienced what oceanographers call turbulent overturning, where entire ocean basins would change their circulation patterns within just a few decades. These rapidly changing ocean currents created atmospheric conditions that were both unpredictable and incredibly violent. Coastal regions could experience tropical conditions one year and near-Arctic temperatures the next, as shifting ocean currents completely reorganized regional climate patterns. The fossil record from post-snowball periods shows evidence of marine organisms that had adapted to cold conditions, suddenly buried under sediments deposited by flash floods, generated by unprecedented rainfall events. The atmospheric chemistry during the post-snowball recovery was also unique in Earth's history. The massive volcanic activity that had ended the glaciation continued to pump gases into the atmosphere long after the ice had melted. creating greenhouse conditions so intense they made the planet uninhabitable for most forms of life. Surface temperatures in some regions exceeded 50 degrees Celsius, while atmospheric humidity levels reached saturation points that made breathing difficult for any organism that relied on air-breathing metabolism. The precipitation patterns during the post-snowball greenhouse were characterized by what climatologists call atmospheric rivers, massive streams of water vapor that could transport the equivalent of entire river systems through the atmosphere. When these atmospheric rivers encountered topographic barriers like mountain ranges, they could dump their entire water content within just a few days, creating flood events that reshaped entire continental drainage systems. But perhaps most remarkably, it was during these post-snowball recovery periods that complex multicellular life first began to evolve on Earth. The extreme climate variability created evolutionary pressures that favored organisms capable of surviving rapid environmental changes, leading to the development of the sophisticated cellular mechanisms that would eventually give rise to all complex life on the planet. The Ediacaran period that followed the last snowball Earth event was characterized by continued climate instability, as Earth's atmospheric system struggled to reach a new equilibrium. The weather during this time was dominated by rapid oscillations between greenhouse and icehouse conditions, creating atmospheric chaos that persisted for tens of millions of years. These climate oscillations created weather patterns that were both more extreme and more variable than anything in Earth's subsequent history. Some regions experienced temperature swings of over 50 degrees Celsius within just a few years, while precipitation patterns could shift from desert conditions to monsoon intensity within a single season. The geological record shows evidence of ecosystems that were repeatedly established and destroyed by these extreme weather events, creating evolutionary pressures that drove the rapid diversification of early complex life. The atmospheric composition during the Ediacaran was also unique, with oxygen levels that fluctuated wildly as the planet's biological systems struggled to establish stable biogeochemical cycles. These oxygen fluctuations created atmospheric conditions that were alternately toxic and life-supporting, driving the evolution of metabolic flexibility that would become crucial for surviving later climate extremes. The transition from the Ediacaran to the Cambrian period marked another major reorganization of Earth's climate system, as the continued fragmentation of ancient supercontinents created ocean circulation patterns that began to resemble modern configurations. But this transition involved weather patterns that were still far more extreme than anything we experience today. The early Cambrian was characterized by what paleoclimatologists call greenhouse, punctuated by icehouse events, where the generally warm global climate was periodically interrupted by rapid cooling episodes that could last for hundreds of thousands of years. These cooling events weren't gradual climate shifts. They were atmospheric catastrophes triggered by massive volcanic eruptions or asteroid impacts that could plunge global temperatures by 20 degrees or more within just a few decades. The weather during these early Cambrian cooling events was dominated by ice storms and blizzards that could persist for decades at a time. The rapid climate transitions created atmospheric instability so severe it generated weather phenomena that operated according to completely different physical principles than modern storms. Some paleoclimatic models suggest the existence of ice hurricanes, rotating storm systems powered by the temperature gradients between frozen and unfrozen regions that could maintain themselves for years at a time. The recovery from these cooling events involved weather patterns that were equally extreme in the opposite direction. As volcanic activity and greenhouse gas accumulation eventually overcame the cooling effects, global temperatures could rise by 30 degrees or more within just a few thousand years. These rapid warming events created atmospheric conditions so unstable they generated hypercanes that could cover entire ocean basins and maintain hurricane-force winds for months at a time. The Ordovician period brought yet another category of weather extremes as atmospheric oxygen levels began to rise toward modern concentrations. The increasing oxygen content created combustion conditions that made wildfires both more frequent and more intense than anything in Earth's previous history. But these weren't just forest fires. The high oxygen levels allowed fires to burn in environments and materials that are completely fireproof under modern atmospheric conditions. Paleobotanical evidence shows that Ordovician fires could burn through wetlands and even underwater in some cases, as the oxygen-rich atmosphere allowed combustion to continue even in environments that were saturated with water. These fires created smoke clouds so dense they could persist in the atmosphere for years, generating their own weather patterns as they slowly circulated around the planet. The electrical activity during Ordovician storms was also unprecedented. The combination of high atmospheric oxygen and the massive smoke clouds from frequent fires created conditions where lightning strikes were not just more common, but fundamentally different in character. Some lightning events appear to have created sustained electrical discharges that could maintain themselves for minutes rather than milliseconds, essentially turning portions of the atmosphere into temporary plasma conduits. The Silurian period that followed was marked by the first appearance of complex terrestrial ecosystems, but the weather conditions during this time remained far more extreme than anything that would support modern land-based life. The atmospheric pressure during the Silurian was significantly higher than today, creating weather dynamics that operated according to different physical principles. The higher atmospheric density meant that wind systems could carry much more kinetic energy than modern weather patterns. Storm fronts moved with such force that they could literally reshape coastlines through purely atmospheric erosion. Geological evidence shows wave-cut platforms from this period that could only have been created by storm surge events that exceeded heights of over 100 feet, generated not by underwater earthquakes, but by atmospheric disturbances of unprecedented intensity. The precipitation chemistry during the Silurian was also unique due to the continuing volcanic activity associated with ongoing continental reorganization. Rainwater during this period contained dissolved minerals and gases that made it significantly more reactive than modern precipitation. This chemically active rainfall could dissolve rock formations within just a few centuries, creating karst landscapes and cave systems at rates that would be impossible under current atmospheric conditions. The Devonian period brought the most dramatic expansion of terrestrial plant life in Earth's history. But this biological revolution occurred against a backdrop of continued climate extremes. The rapid expansion of forest ecosystems created feedback loops that destabilized atmospheric chemistry in ways that generated weather patterns unlike anything before or since. As vast forests spread across the continents, they began pulling enormous amounts of carbon dioxide out of the atmosphere through photosynthesis. But this biological carbon sequestration happened so rapidly that it created atmospheric instability that manifested as extreme weather variability. Climate conditions could shift from tropical to temperate to near Arctic within just a few decades, creating evolutionary pressures that drove rapid speciation among both plant and animal communities. The storm systems during the Devonian were powered by atmospheric chemistry that was constantly changing as biological processes altered the composition of the atmosphere. Unlike modern storms that operate in relatively stable atmospheric conditions, Devonian weather systems had to adapt to changing gas concentrations that could alter fundamental atmospheric physics from season to season. The late Devonian extinction that we discussed earlier was just one example of how these biological atmospheric feedbacks could create climate catastrophes. The interaction between expanding terrestrial ecosystems and atmospheric chemistry created conditions where small changes in biological productivity could trigger massive shifts in global weather patterns, leading to climate instability that persisted for millions of years. The Carboniferous period that followed brought atmospheric conditions that created the most alien fire behavior in Earth's history. With oxygen concentrations reaching 35% of the atmosphere, combustion occurred with intensities and in environments that seem almost impossible by modern standards. But it wasn't just the fires themselves that were extreme. The weather patterns created by these super intense fires were equally extraordinary. The massive fires burning across Carboniferous landscapes created their own atmospheric circulation patterns. Fire-generated updrafts were so powerful they could create pyrocumulonimbus clouds that reached altitudes of over 40 miles, well into what we now call the mesosphere. These fire-driven storm systems could generate lightning strikes so intense they could fuse sand into glass across areas covering hundreds of square miles. The smoke from Carboniferous fires contained vaporized metals and minerals that, when they condensed back out of the atmosphere, created precipitation events that were literally metallic in composition. Some regions experienced rainfall where dissolved copper, iron, and other metals precipitated out of the atmosphere in concentrations high enough to create ore deposits that are still mined today. The wind patterns during the Carboniferous were also affected by the unique atmospheric composition. The higher oxygen and carbon dioxide concentrations created atmospheric density variations that generated wind systems with characteristics unlike modern weather patterns. Some paleoclimatic models suggest the existence of atmospheric rivers that could transport not just water vapor, but also particulate matter, including metals and minerals, across entire continents. The Permian period brought the most extreme continental climate conditions in Earth's history, as the assembly of Pangaea created landmass configurations that have never been repeated. The weather patterns generated by this massive supercontinent were so extreme they created their own unique atmospheric phenomena that operated according to principles we're still trying to understand. The seasonal monsoons that developed around Pangaea were continental in scale, drawing moisture from oceans thousands of miles away and concentrating it into precipitation events that could reshape entire mountain ranges within just a few seasons. These weren't just heavy rains, they were atmospheric phenomena that operated more like slow-motion tsunamis of water vapor, carrying enough energy to carve out canyon systems hundreds of miles long within just a few thousand years. The dust storms generated by Pangaea's extreme continental climate were equally unprecedented. The vast interior regions of the supercontinent experienced such extreme aridity that surface materials were essentially powdered by constant freeze-thaw cycles and temperature variations. When these pulverized materials were finally mobilized by wind systems, they created dust clouds so massive they could circle the entire planet multiple times before finally settling back to the surface. But it was the transition from Pangaea's extreme continental conditions to the volcanic catastrophe that ended the Permian that created the most alien weather patterns in Earth's entire climate history. The Siberian Traps volcanism didn't just release lava and gas. It created atmospheric conditions that were fundamentally different from anything that had existed before or has existed since. The volcanic emissions created atmospheric chemistry that made normal weather processes impossible. The combination of volcanic gases, aerosols, and particulates created conditions where water vapor could not condense normally, leading to atmospheric supersaturation that persisted for thousands of years. When precipitation finally did occur, it often took the form of chemically reactive droplets that were toxic to most forms of life. The electrical activity during the end Permian volcanic crisis was unlike anything else in the geological record. The massive amounts of particulate matter in the atmosphere created conditions where electrical charges could build up to levels that generated continuous lightning activity across entire continents. Some regions experienced electrical storms that persisted for months at a time, with lightning strikes so frequent they created electromagnetic effects that influenced mineral formation processes in ways that are still visible in rock formations today. The weather patterns during the end Permian extinction represent the absolute extreme of what Earth's atmospheric system can produce while still maintaining conditions where liquid water can exist at the surface. The combination of extreme temperatures, toxic atmospheric chemistry, and chaotic circulation patterns created a planetary environment that was essentially uninhabitable for most forms of life, yet still retained the basic physical characteristics of a planetary atmosphere.
Hey.
The recovery from the end Permian extinction involved weather patterns that were equally extreme, as Earth's climate system struggled to re-establish stable operating conditions. The early Triassic was characterized by continued atmospheric instability, as volcanic activity gradually decreased and biological systems slowly began to recolonize the devastated planet. The weather during this recovery period was dominated by what climatologists call environmental oscillations, where different regions of the planet would experience rapid switches between completely different climate regimes. A location that experienced desert conditions for decades could suddenly shift to tropical rainforest conditions within just a few years, then switch back just as rapidly. These rapid environmental changes created evolutionary pressures that drove the development of the adaptive strategies that would eventually allow dinosaurs and other archosaur groups to dominate terrestrial ecosystems for the next 180 million years. The extreme climate variability of the early Triassic essentially served as an evolutionary testing ground that favored organisms capable of surviving rapid and unpredictable environmental changes. The study of these prehistoric weather extremes continues to reveal new details about the fundamental limits of how extreme Earth's climate system can become, while still supporting life. Each new paleoclimatic discovery pushes our understanding of atmospheric physics into new territory, showing us weather patterns that operated according to principles we're only beginning to comprehend. Recent advances in analyzing ancient atmospheric chemistry have revealed evidence of weather phenomena that challenge our basic understanding of how planetary atmospheres are supposed to work. Some prehistoric atmospheric conditions created weather patterns that seem to violate fundamental physical principles, until we realize that they actually represent extreme cases of atmospheric behavior that are theoretically possible but have never been observed in modern systems. The techniques scientists use to reconstruct these ancient weather patterns continue to evolve, providing ever more detailed pictures of climate conditions that existed hundreds of millions of years ago. New methods of analyzing microscopic mineral inclusions in ancient rocks are revealing daily weather patterns from deep geological time, showing us that prehistoric climate variability extended down to timescales of individual storm events. These discoveries are not just filling in details about ancient climate history, they're revealing fundamental principles about how planetary atmospheres respond to extreme conditions. Knowledge that has applications ranging from understanding climate dynamics on Earth to predicting atmospheric behavior on exoplanets orbiting other stars. The prehistoric weather patterns we've explored represent just a small sample of the incredible variety of climate conditions that have existed throughout Earth's long atmospheric history. Every new fossil discovery, every advance in analytical techniques, every improvement in climate modeling reveals additional examples of weather extremes that push the boundaries of what we thought was possible on a planet like Earth. As we continue to study these ancient climate systems, we gain a deeper appreciation for both the incredible power and the remarkable adaptability of Earth's atmospheric processes. The story of prehistoric weather is ultimately a testament to the dynamic nature of planetary systems and the incredible resilience of life in the face of environmental conditions that seem almost impossibly extreme by modern standards. The sheer scale of these atmospheric transformations becomes even more staggering when we examine how prehistoric weather systems could maintain extreme conditions for geological time periods that dwarf human comprehension. During the Middle Jurassic, roughly 170 million years ago, Earth experienced what paleoclimatologists now recognize as the most sustained period of atmospheric hyperactivity in the planet's recorded history. Unlike the brief but intense climate catastrophes we've discussed, the Middle Jurassic weather patterns maintained their extreme characteristics for over 20 million consecutive years. This wasn't just a long hot spell or an extended stormy period. This was a fundamental reorganization of how Earth's atmosphere distributed energy, creating weather systems that operated according to principles we're still struggling to fully understand. The atmospheric carbon dioxide concentrations during this period reached levels that were consistently 4 to 6 times higher than modern values. But it was the stability of these extreme concentrations that created truly alien weather conditions. Modern climate systems are characterized by variability and change, but Middle Jurassic atmospheric chemistry remained locked in configurations that generated the same types of extreme weather decade after decade, century after century. The storm systems during this period weren't just larger or more intense than modern hurricanes. They were fundamentally different phenomena that could maintain their structure and intensity while traveling across entire ocean basins. Paleoclimatic reconstructions suggest that some Middle Jurassic storm systems persisted for months at a time, slowly migrating around the planet like permanent atmospheric features. These hyper-persistent storms were powered by ocean surface temperatures that regularly exceeded 35 degrees Celsius, even in polar regions. The thermal energy available to drive atmospheric circulation was so enormous that weather systems could maintain hurricane-force winds while covering areas larger than modern continents. The geological record preserves evidence of storm deposits from this period that indicate individual weather events transported sediment across distances of over 3,000 miles. But perhaps most remarkably, the Middle Jurassic atmosphere developed what atmospheric physicists call thermal stratification patterns that created multiple distinct weather layers operating simultaneously at different altitudes. Surface storms might be generating winds in one direction, while atmospheric circulation at 10,000 feet moved in completely different patterns, and stratospheric winds followed yet another set of circulation rules. This multi-layered atmospheric structure created precipitation patterns that were incredibly complex and unpredictable. Some regions experienced what paleoclimatologists describe as precipitation cascades, where moisture would condense and re-evaporate multiple times as it moved through different atmospheric layers before finally reaching the ground. The result was rainfall that could vary in intensity by orders of magnitude within just a few miles of geographic distance. The chemical composition of Middle Jurassic precipitation was also unique due to the extreme atmospheric conditions. The superheated ocean surfaces released not just water vapor, but also dissolved minerals and organic compounds that became incorporated into the atmospheric moisture. When this chemically loaded water vapor finally condensed, it created rainfall that was essentially a dilute mineral solution, rich in nutrients that fueled explosive plant growth, but also corrosive enough to rapidly weather rock formations. The lightning activity during Middle Jurassic storms exceeded anything in the modern world by several orders of magnitude. The combination of extreme atmospheric moisture, elevated temperatures, and complex multi-layered circulation patterns created electrical charge separation on a scale that generated lightning strikes with energies comparable to small nuclear explosions. Some lightning events appear to have created fulgurite formations that extended for miles underground, indicating electrical discharges that could penetrate deep into bedrock formations. The wind patterns during this period were equally extraordinary. The minimal temperature gradients between equatorial and polar regions meant that atmospheric circulation was driven almost entirely by convective processes, rather than the pressure gradients that dominate modern weather systems. This created wind patterns that were both more chaotic and more energetic than contemporary weather, with paleoclimatic models suggesting that sustained wind speeds regularly exceeded 150 miles per hour across vast areas of the planet. The dust transport during the Middle Jurassic was also unprecedented in scale. The extreme wind systems could lift and transport particulate matter across intercontinental distances, creating atmospheric dust loading that significantly affected global climate patterns. Some dust clouds from this period appear to have remained suspended in the atmosphere for years at a time, slowly circling the planet multiple times before finally settling back to the surface. The transition out of these Middle Jurassic hyper-greenhouse conditions marked another dramatic shift in Earth's climate system, as volcanic activity and changing ocean circulation patterns began to moderate the extreme atmospheric conditions. But this wasn't a gradual cooling. Instead, it was a series of rapid climate oscillations that created some of the most chaotic weather patterns in the geological record. During the late Jurassic, paleoclimatic evidence shows that global climate conditions could shift between different stable states within just a few thousand years. These weren't minor temperature adjustments. They were complete reorganizations of atmospheric circulation patterns that could transform regional climates from tropical to temperate conditions within just a few human generations. The storm systems during these late Jurassic climate transitions were characterized by what meteorologists call atmospheric resonance effects, where weather patterns would become locked into oscillating cycles that could persist for decades. Some regions experienced alternating periods of intense storm activity, followed by extended calm periods, with the transitions between these states happening so rapidly they could occur within just a few seasons. The precipitation patterns during these climate oscillations were equally erratic. Some areas experienced what geologists call mega drought cycles, where rainfall could essentially cease for centuries at a time, followed by deluge periods when decades' worth of normal precipitation would fall within just a few years. The erosion patterns created by these extreme precipitation cycles carved out landscape features that are still visible today, including canyon systems that were excavated entirely during brief periods of intense rainfall. The atmospheric chemistry during the late Jurassic was also highly unstable due to the ongoing volcanic activity associated with the breakup of Pangaea. Different regions of the atmosphere could have significantly different chemical compositions, creating weather patterns that operated according to varying physical principles, depending on local atmospheric conditions. The Cretaceous period that followed brought yet another category of weather extremes, as the planet's ocean circulation patterns underwent major reorganizations due to continued continental drift. The opening of new ocean basins and the closure of others created atmospheric oceanic interactions that generated weather systems unlike anything in Earth's previous climate history. The early Cretaceous was characterized by what oceanographers call thermohaline instability, where ocean circulation patterns would periodically collapse and reorganize themselves within just a few decades. These oceanic reorganizations had immediate and dramatic effects on atmospheric circulation, creating weather whiplash effects, where regional climates could change completely within just a few years. The storm systems generated by these oceanic reorganizations were powered by temperature gradients that could develop and disappear within just a few seasons. Unlike modern weather systems that operate within relatively stable oceanic conditions, early Cretaceous storms had to adapt to constantly changing oceanic heat sources, creating atmospheric dynamics that were both unpredictable and incredibly energetic. The marine environments during this period also contributed to atmospheric instability in ways that have no modern parallels. The rapid changes in ocean circulation created regions where deep ocean waters would suddenly surface, bringing with them dissolved gases and nutrients that had been trapped in deep ocean reservoirs for millions of years. When these ancient waters reached the surface, they released massive amounts of carbon dioxide and hydrogen sulfide into the atmosphere, creating localized atmospheric conditions that were toxic to most forms of life. The weather patterns created by these oceanic outgassing events were dominated by what atmospheric chemists call reactive precipitation, where rainwater contained dissolved gases that made it chemically aggressive. This reactive rainfall could dissolve limestone formations within decades and created soil conditions that were alternately highly acidic and highly basic, depending on which gases were being released from the oceans. The mid-Cretaceous thermal maximum represents perhaps the most extreme example of sustained greenhouse conditions in Earth's climate record. During this period, global temperatures were so elevated that the normal mechanisms that regulate Earth's climate system essentially shut down. creating atmospheric conditions that operated according to completely different principles than modern weather patterns. The ocean temperatures during the thermal maximum reached levels that eliminated the density differences that normally drive oceanic circulation. Without these density gradients, ocean currents became sluggish and unpredictable, creating atmospheric conditions where regional weather patterns could persist unchanged for centuries at a time. Some areas experienced permanent high-pressure systems that prevented rainfall for hundreds of years, while other regions were dominated by persistent low-pressure systems that generated continuous storm activity. The atmospheric moisture content during the thermal maximum was so high that it fundamentally altered how weather systems could form and maintain themselves. With humidity levels regularly exceeding 70%, the atmosphere was essentially saturated with water vapor, creating conditions where precipitation could occur without the formation of traditional storm systems. Some regions experienced what climatologists call vapor precipitation, where water would condense directly out of the atmosphere without any apparent meteorological trigger. The electrical activity during the thermal maximum was also unprecedented due to the extreme atmospheric moisture content. The combination of high humidity and elevated temperatures created conditions where electrical charges could build up to levels that generated continuous aurora-like phenomena at ground level. Some paleomagnetic studies suggest that electrical activity during this period was so intense it created temporary magnetic field disturbances that affected mineral formation processes across entire continents. The wind patterns during the mid-Cretaceous were dominated by convective processes that created atmospheric circulation systems unlike anything in the modern world. The extreme heating of ocean surfaces generated updrafts so powerful they could transport moisture and particulate matter into the stratosphere on a routine basis. These stratospheric injections created atmospheric mixing patterns that distributed materials around the planet in ways that have no contemporary equivalent. The dust transport during this period was equally remarkable. The extreme convective activity could lift material from ground level to altitudes of over 20 miles, where it would be caught in stratospheric wind patterns and transported around the globe. Some dust particles from the mid-Cretaceous appear to have remained suspended in the atmosphere for decades, slowly settling back to Earth over vast geographic areas. The transition out of the mid-Cretaceous thermal maximum involved weather patterns that were among the most violent in Earth's climate history. As ocean circulation patterns finally began to re-establish themselves, the atmospheric energy that had been building up in the stagnant climate system was suddenly released in a series of catastrophic weather events that reshaped continental landscapes within just a few thousand years. The late Cretaceous period was characterized by what paleoclimatologists call climate flickering, where global weather patterns would rapidly oscillate between different stable configurations. These oscillations weren't gradual transitions. They were sudden shifts that could completely transform regional climates within just a few decades, creating evolutionary pressures that drove rapid speciation among both plant and animal communities. The storm systems during these late Cretaceous climate oscillations were characterized by extreme variability in both intensity and duration. Some storms could maintain hurricane-force winds for weeks at a time, while others would develop and dissipate within just a few hours. The unpredictability of these weather patterns made it nearly impossible for ecosystems to establish stable configurations, leading to constant evolutionary pressure for adaptive flexibility. The precipitation patterns during the late Cretaceous were equally chaotic. Some regions experienced precipitation events so intense they could deposit several feet of water within just a few hours, followed by drought periods that could last for years. The alternation between these extreme wet and dry phases created erosion patterns that carved out landscape features at rates that would be impossible under modern climate conditions. The atmospheric pressure variations during this period were also extreme due to the rapid climate oscillations. Barometric pressure could change by amounts equivalent to the difference between sea level and high mountain altitudes within just a few days, creating physiological stress for organisms that were adapted to stable pressure conditions. The final phase of the Cretaceous period, leading up to the asteroid impact that ended the age of dinosaurs, was marked by increasing climate instability as volcanic activity from the Deccan Traps began to alter atmospheric chemistry. The combination of ongoing climate oscillations and increasing volcanic emissions created weather conditions that were becoming increasingly chaotic and unpredictable, even before the impact event occurred. The Deccan volcanism created atmospheric conditions that were already stressing global ecosystems when the asteroid impact provided the final catastrophic shock to Earth's climate system. The combination of these two factors created weather patterns during the end Cretaceous extinction that were more extreme than either factor could have produced alone. The immediate aftermath of the Chicxulub impact created weather conditions that represent the absolute extreme of what Earth's atmospheric system can produce. The impact debris that re-entered the atmosphere generated temperatures hot enough to ignite organic matter across the entire planet simultaneously, creating a global firestorm that consumed virtually all above-ground biomass within just a few hours. The smoke and ash from these global fires combined with impact debris to create atmospheric conditions where sunlight was reduced to less than 1% of normal levels for over 6 months. But this wasn't just a simple reduction in solar radiation. The particles suspended in the atmosphere created optical effects that turned the sun into a dim red disk, barely visible through the atmospheric haze, creating lighting conditions unlike anything else in Earth's history. The weather patterns during the impact winter were powered entirely by thermal energy stored in the oceans and ongoing geothermal activity. Without solar heating to drive normal atmospheric circulation, weather systems became completely chaotic and unpredictable. Some regions experienced simultaneous snow and volcanic ash falls, creating precipitation that was both frozen and chemically reactive. The atmospheric chemistry during the impact winter was toxic in ways that challenged the survival mechanisms of even the most adaptable organisms. The combination of impact debris, volcanic emissions, and smoke from global fires created atmospheric conditions where the air itself was poisonous to most forms of life that depended on aerobic respiration. The recovery from impact winter conditions involved weather patterns that were equally extreme as the atmospheric debris finally began to settle and sunlight returned to Earth's surface. The accumulated greenhouse gases from the global fires and impact-triggered volcanism created warming so rapid it generated atmospheric instability that persisted for thousands of years after the initial impact event. The Paleocene period that followed the extinction was characterized by continued weather chaos as Earth's climate system struggled to establish new stable operating conditions. The disruption of normal atmospheric and oceanic circulation patterns had been so severe that it took millions of years for weather patterns to return to anything resembling the relatively stable conditions that had characterized much of the Mesozoic era. The study of these prehistoric weather extremes reveals that Earth's atmospheric system is capable of operating in modes that are fundamentally different from anything we observe in the modern world. The relatively stable climate conditions that have characterized recent geological time represent just one possible configuration of how planetary atmospheres can organize themselves. Understanding these ancient weather patterns provides crucial insights into the fundamental physics of atmospheric systems and how they respond to extreme perturbations. Each new paleoclimatic discovery reveals another aspect of the incredible complexity and adaptability of Earth's climate system, showing us that our planet's atmosphere has operated according to principles we're only beginning to understand. The techniques used to study these prehistoric weather patterns continue to advance, providing ever more detailed reconstructions of atmospheric conditions from hundreds of millions of years ago. New methods of analyzing ancient atmospheric chemistry are revealing weather phenomena that challenge our basic understanding of how planetary atmospheres are supposed to behave under extreme conditions. These discoveries are not just academic curiosities. They provide essential knowledge about how complex atmospheric systems respond to rapid changes in energy inputs, chemical composition, and boundary conditions. This understanding has applications ranging from predicting climate responses to anthropogenic changes, to modeling atmospheric behavior on planets orbiting other stars. The prehistoric weather extremes we've explored represent a comprehensive catalogue of the most intense atmospheric conditions that can occur on a planet like Earth, while still maintaining liquid water at the surface. These ancient climate systems pushed the boundaries of atmospheric physics to their absolute limits, creating weather patterns that seem almost alien to our modern experience, but represent natural expressions of fundamental physical processes operating under extreme conditions. As we continue to uncover new evidence of these ancient atmospheric catastrophes, we gain a deeper appreciation for both the incredible power of natural forces and the remarkable resilience of life itself. The story of prehistoric weather is ultimately a testament to the dynamic nature of planetary systems and the incredible capacity for adaptation that has allowed life to survive and thrive, despite facing environmental conditions that seem almost impossibly extreme by contemporary standards. The truly mind-bending aspect of these prehistoric atmospheric systems becomes even more apparent when we examine how they created feedback loops that could amplify weather extremes far beyond what simple physics would predict. During the Eocene epoch, about 50 million years ago, Earth experienced what geologists now call the Paleocene-Eocene thermal maximum. But this event was just the most dramatic example of how prehistoric climate systems could enter runaway acceleration modes that have no modern equivalent. The thermal maximum wasn't triggered by a single catastrophic event like an asteroid impact or massive volcanic eruption. Instead, it was caused by what climatologists call a cascade failure in the planet's carbon cycle, where warming temperatures triggered the release of methane from ocean sediments, which caused more warming, which released more methane, creating a feedback loop that spiraled out of control for tens of thousands of years. The methane releases during this period were absolutely staggering in scale. We're talking about billions of tons of methane bubbling up from ocean floors across the entire planet simultaneously. When this methane reached the atmosphere, it created greenhouse conditions so intense that global temperatures rose by at least 8 degrees Celsius, and possibly as much as 12 degrees within just 20,000 years. But here's what makes this event truly extraordinary from a meteorological perspective. The massive methane releases didn't just warm the planet uniformly, they created atmospheric chemistry that fundamentally altered how weather systems could form and behave. Methane has very different optical properties than carbon dioxide, and when atmospheric concentrations reached the levels seen during the thermal maximum, they created greenhouse effects that operated according to different physical principles than modern climate systems. The storm systems during the thermal maximum were powered by atmospheric energy densities that exceeded anything in Earth's climate record. The combination of extreme surface heating and altered atmospheric chemistry created convective processes so intense they could transport material from ground level directly into the stratosphere without passing through the normal atmospheric layers. This created weather patterns that were essentially three-dimensional, with storm systems that extended from the Earth's surface all the way to the edge of space. The precipitation events during this period were equally unprecedented. The superheated atmosphere could hold enormous amounts of water vapor, but when atmospheric conditions finally reached saturation, the resulting rainfall was measured not in inches per hour, but in feet per hour. Paleosol studies show evidence of individual storm events that deposited over 20 feet of water within just a few days, creating flash floods that carved out river valleys hundreds of miles long within single seasons. The wind patterns during the thermal maximum were dominated by what atmospheric physicists call hypercells, massive convective systems that could maintain themselves for months at a time, while slowly migrating across continents. These weren't just big thunderstorms. They were atmospheric phenomena that operated more like slow-moving hurricanes over land, generating sustained winds that regularly exceeded 200 miles per hour while covering areas larger than modern countries. The electrical activity during these hypercell events was beyond anything we can observe in modern weather systems. The extreme convective activity created charge separation on a scale that generated lightning strikes with energies comparable to nuclear weapons. Some lightning events from this period created fulgurite formations that extended for dozens of miles underground, indicating electrical discharges that could penetrate through solid bedrock and create underground plasma channels. The ocean conditions during the thermal maximum created their own unique weather phenomena as surface temperatures reached levels that would be instantly lethal to most modern marine life. In tropical regions, ocean surface temperatures regularly exceeded 42 degrees Celsius, creating evaporation rates so high that atmospheric humidity levels approached 100% across vast areas of the planet. These extreme humidity conditions created weather patterns that have no modern equivalent. Instead of the familiar cycle of evaporation, cloud formation, and precipitation that characterizes today's weather, the thermal maximum atmosphere was so saturated with moisture that water would condense and re-evaporate multiple times before finally reaching the ground. This created precipitation cascades where the same water molecules could participate in dozens of separate weather events as they slowly worked their way down through the supersaturated atmosphere. The atmospheric pressure variations during this period were also extreme due to the altered atmospheric chemistry. The high concentrations of methane and water vapor created density variations that generated pressure waves that could travel across entire continents within just a few days. These pressure waves weren't just meteorological curiosities. They were powerful enough to trigger landslides, avalanches, and even earthquakes as they passed over geologically unstable regions. The dust transport during the thermal maximum was equally remarkable due to the extreme convective activity. The hypercell systems could lift material from desert regions and transport it across intercontinental distances, creating atmospheric dust loading that significantly affected global weather patterns. Some dust clouds from this period appear to have circled the planet multiple times, creating their own weather systems as they slowly settled back to Earth over periods of years. The transition out of the thermal maximum conditions involved weather patterns that were among the most chaotic in Earth's climate history. As ocean temperatures finally began to moderate and methane concentrations started to decline, the atmospheric energy that had been driving the extreme weather systems was suddenly released in a series of catastrophic events that reshaped global climate patterns within just a few thousand years. The Middle Eocene period that followed was characterized by what climatologists call atmospheric reorganization, where global weather patterns underwent fundamental changes as the climate system adapted to post-thermal maximum conditions. This wasn't a gradual return to normal weather. Instead, it was a series of rapid shifts between different atmospheric configurations, each creating its own unique set of extreme weather patterns. During this reorganization period, some regions experienced what paleoclimatologists call climate whiplash, where weather patterns could shift between completely different regimes within just a few decades. Areas that had experienced tropical conditions for thousands of years could suddenly shift to temperate or even Arctic climates within a single human lifetime, then shift back just as rapidly. The storm systems during the Middle Eocene were characterized by extreme unpredictability as atmospheric circulation patterns struggled to establish stable configurations. Unlike modern weather systems that operate within relatively predictable seasonal cycles, Middle Eocene storms could develop and intensify according to completely different principles depending on local atmospheric conditions that were constantly changing. The precipitation patterns during this period were equally erratic. Some areas experienced megadrought conditions that could persist for centuries, followed by deluge periods when decades' worth of normal rainfall would fall within just a few seasons. The geological record shows evidence of landscape features that were carved out entirely during brief periods of intense precipitation, including canyon systems that were excavated within just a few thousand years. The late Eocene brought yet another category of weather extremes as global cooling began to set in, and the first Antarctic ice sheets started to form. The transition from the extreme greenhouse conditions of the thermal maximum to the icehouse conditions that would characterize much of the subsequent climate history involved weather patterns that were uniquely violent and unpredictable. The formation of the first major ice sheets in over 50 million years created atmospheric circulation patterns that had no precedent in Earth's recent climate history. The temperature gradients between the newly frozen Antarctic regions and the still warm tropical oceans were so extreme they generated storm systems with characteristics unlike anything that had existed during the preceding greenhouse periods. These early icehouse storms were powered by temperature differences that regularly exceeded 60 degrees Celsius between different regions of the planet. The resulting weather systems were characterized by winds that could maintain hurricane force intensity while traveling across entire ocean basins, creating wave systems that regularly exceeded heights of 100 feet, even in deep ocean regions, far from any landmasses. The precipitation patterns associated with these early icehouse conditions were dominated by what glaciologists call ice rain events, where atmospheric moisture would freeze into ice crystals at high altitudes and then partially melt as it fell through warmer air layers closer to the surface. This created precipitation that was simultaneously frozen and liquid, generating weather phenomena that were both more destructive and more unpredictable than either pure snow or pure rain. The Oligocene period that followed marked the establishment of permanent Antarctic ice sheets and the beginning of the icehouse climate conditions that would dominate Earth's subsequent climate history. But the transition into these icehouse conditions involved weather patterns that were far more extreme than the relatively stable glacial and interglacial cycles that would characterize later Ice Age periods. During the early Oligocene, the atmospheric circulation patterns were still adjusting to the presence of major ice sheets in the southern hemisphere. The interaction between ice-covered Antarctica and the still warm Arctic regions created asymmetric atmospheric circulation that generated weather patterns unlike anything in Earth's climate record. The storm tracks during this period were characterized by what meteorologists call meridional flow patterns, where atmospheric circulation followed north-south paths rather than the east-west patterns that dominate modern weather systems. These meridional flows created weather conditions where tropical air masses could penetrate deep into polar regions, while Arctic air could suddenly appear in tropical latitudes, creating temperature swings that could exceed 40 degrees Celsius within just a few days. The precipitation chemistry during the Oligocene was also affected by the changing atmospheric circulation patterns. The new storm tracks brought different air masses into contact with each other, creating atmospheric mixing that generated chemically reactive precipitation. This reactive rainfall could alter soil chemistry within decades and created erosion patterns that carved out landscape features at rates far exceeding anything possible under modern climate conditions. The late Oligocene marked the beginning of the first major glacial advances in the Northern Hemisphere, creating atmospheric conditions that would become the template for the Ice Age cycles that would dominate the next 30 million years of Earth's climate history. But these early glacial advances were far more chaotic and unpredictable than the relatively regular glacial cycles that would characterize the later Pleistocene ice ages. The weather patterns during these early glacial advances were dominated by what glaciologists call ice sheet instability, where massive ice formations would grow and collapse on timescales of just a few thousand years. These rapid ice sheet fluctuations created atmospheric disturbances that generated weather systems of unprecedented violence and unpredictability. When major ice sheets collapsed, they released enormous volumes of fresh water into the oceans within just a few centuries, creating oceanic conditions that disrupted global circulation patterns and generated atmospheric chaos that could persist for thousands of years. The weather during these ice sheet collapse events was characterized by storm systems that could maintain themselves for decades while slowly migrating around the planet, creating permanent regions of extreme weather that prevented normal ecological succession. The Miocene period brought a temporary return to warmer conditions as atmospheric carbon dioxide levels rose due to increased volcanic activity. But this Miocene warming was characterized by weather patterns that were fundamentally different from the earlier Eocene thermal conditions, creating atmospheric phenomena that represented entirely new categories of climate extremes. The Miocene climate optimum, about 15 million years ago, was marked by the development of what paleoclimatologists call regional hypergreenhouse conditions, where certain areas of the planet experienced extremely intense warming while others remained relatively cool. This created temperature gradients that were far steeper than anything in the modern world, generating weather systems that were powered by unprecedented amounts of atmospheric energy. The storm systems during the Miocene optimum were characterized by what meteorologists call thermal bombs, rapidly developing weather systems that could intensify from calm conditions to hurricane-force winds within just a few hours. These weren't just fast-moving storms. They were atmospheric phenomena that could generate wind speeds exceeding 300 miles per hour while maintaining their intensity across vast geographic areas. The precipitation patterns during this period were equally extreme. The intense regional heating created atmospheric moisture distributions that were highly concentrated in certain areas, while leaving others completely arid. Some regions experienced precipitation rates that exceeded anything in the geological record, while areas just a few hundred miles away could go without rainfall for decades at a time. The late Miocene marked the beginning of the final transition into the Ice Age climate conditions that would dominate the most recent portion of Earth's climate history. But this transition involved weather patterns that were far more extreme than the relatively gentle cooling that most people associate with the onset of Ice Age conditions. The atmospheric circulation during the late Miocene was characterized by what climatologists call circulation collapse, where established weather patterns would suddenly break down and reorganize themselves according to completely different principles. These circulation collapses could happen within just a few years, creating weather chaos that would persist for centuries as new atmospheric patterns struggled to establish themselves. The storm systems during these circulation collapse events were among the most violent in Earth's climate record. The breakdown of established atmospheric patterns released enormous amounts of stored atmospheric energy in the form of weather systems that could maintain hurricane-force winds for months at a time, while covering areas larger than entire continents. The Pliocene period brought the establishment of the basic atmospheric circulation patterns that would characterize the subsequent Ice Age cycles. But these early Ice Age conditions were still far more extreme than the relatively stable glacial and interglacial periods that would define the later Pleistocene climate. The early Pliocene was marked by what glaciologists call ice sheet initialization, where permanent ice formations began to establish themselves in both hemispheres simultaneously. The interaction between these newly formed ice sheets created atmospheric circulation patterns that had never existed before in Earth's climate history, generating weather systems that were uniquely adapted to operating in a world with permanent polar ice. These early Ice Age weather systems were characterized by extreme seasonal variability as the atmospheric circulation adjusted to the dramatic changes in surface reflectivity caused by expanding ice sheets. Some regions experienced seasonal temperature swings that exceeded 70 degrees Celsius as the ice sheets alternately reflected and absorbed solar radiation, depending on seasonal snow cover and ice formation patterns. The precipitation patterns during the early Pliocene were dominated by what climatologists call ice-enhanced precipitation, where the presence of ice sheets created atmospheric conditions that concentrated moisture into extremely intense but geographically limited precipitation events. Some areas experienced snowfall rates that could deposit several feet of snow within just a few hours, while regions just outside these precipitation zones remained completely dry. The late Pliocene marked the beginning of the regular glacial and interglacial cycles that would define the Pleistocene ice ages. But even these relatively stable climate oscillations involved weather patterns that were far more extreme than anything in recent human experience. The transition between glacial and interglacial conditions involved atmospheric reorganizations that created weather chaos lasting for thousands of years. The study of these prehistoric weather extremes reveals that Earth's atmospheric system has operated in modes that are fundamentally different from anything we observe today. The relatively stable climate conditions that have characterized the last few thousand years represent just a tiny fraction of the weather patterns that our planet's atmosphere is capable of generating. Understanding these ancient climate systems provides crucial insights into the fundamental physics of how atmospheric systems respond to extreme perturbations and changing boundary conditions. Each new paleoclimatic discovery reveals another aspect of the incredible complexity and variability of Earth's climate system, showing us that our planet's atmosphere has operated according to principles that challenge our basic understanding of meteorological physics. The techniques used to study these prehistoric weather patterns continue to evolve, providing increasingly detailed reconstructions of atmospheric conditions from tens of millions of years ago. New methods of analyzing microscopic fossils and chemical isotopes are revealing daily weather patterns from deep geological time, showing us that prehistoric climate variability extended down to the timescale of individual storm events. These discoveries are revolutionizing our understanding of how planetary atmospheres can respond to changing conditions and are providing essential knowledge for predicting how complex climate systems might behave under future scenarios. The prehistoric climate record serves as a natural laboratory for studying atmospheric dynamics under conditions that would be impossible to replicate through any other means. The story of prehistoric weather represents one of the most remarkable chapters in Earth's long environmental history, revealing atmospheric conditions that pushed the boundaries of what we thought was possible on a planet capable of supporting life. These ancient weather systems demonstrate both the incredible power of natural forces and the remarkable adaptability of Earth's climate system in the face of extreme perturbations that would seem catastrophic by modern standards. The most extraordinary revelation about prehistoric weather comes when we examine how these ancient atmospheric systems created evolutionary pressures that literally sculpted the tree of life itself. Throughout Earth's tumultuous climate history, the organisms that survived weren't just lucky. They were forged in the furnace of meteorological chaos, developing survival strategies so sophisticated they seem almost engineered for catastrophe. Take the case of early mammals during the Paleocene recovery period. These weren't the small, timid creatures hiding in burrows that popular imagination often depicts. Fossil evidence reveals mammals that had evolved remarkably complex behavioral adaptations specifically designed to survive the rapid climate oscillations that characterized post-extinction weather patterns. Some species developed the ability to enter extended torpor states that could last for months, essentially allowing them to sleep through the most severe weather events. But it gets even more fascinating when we look at the plant communities that emerged during these chaotic periods. Paleobotanical studies have revealed flowering plants that evolved seed dispersal mechanisms specifically adapted to the extreme wind systems of their time. Some species produce seeds with aerodynamic properties that could keep them airborne for weeks, allowing them to ride out massive storm systems and colonize new territories thousands of miles away when conditions finally calmed. The marine ecosystems tell an equally remarkable story of adaptation to prehistoric weather extremes. During periods when ocean temperatures reached levels that would be instantly lethal to modern marine life, ancient species evolved heat shock proteins so sophisticated they could essentially repair cellular damage in real time. These weren't gradual evolutionary adaptations developed over millions of years. Genetic analysis suggests some of these protective mechanisms evolved within just a few thousand generations, representing evolutionary change at speeds that challenge our understanding of how quickly life can adapt. The fossil record from the Eocene thermal maximum reveals perhaps the most dramatic example of weather-driven evolution. As atmospheric conditions became increasingly toxic due to massive methane releases, some plant species evolved the ability to process and neutralize atmospheric toxins through their root systems. These plants essentially became living air purifiers, creating localized zones of breathable atmosphere that allowed other organisms to survive the worst atmospheric conditions in Earth's history. So here we are, At the end of our journey through Earth's most extreme weather history, we've witnessed atmospheric chaos that makes our worst hurricanes look like gentle spring showers, volcanic winters that could freeze entire continents solid, and greenhouse conditions so intense they turned the planet into something almost unrecognizable. The next time you step outside and complain about a heat wave or a thunderstorm, just remember that you're living through the calmest, most stable climate period our planet has experienced in hundreds of millions of years. The prehistoric weather we've explored tonight wasn't just meteorological curiosity. It was the forge that shaped all life on Earth, including us. Every breath you take, every adaptation that allows you to survive in this world, carries the genetic memory of organisms that endured atmospheric conditions so extreme they seem like science fiction. And while we may never face anything approaching these prehistoric weather catastrophes, understanding them gives us a profound appreciation for just how dynamic and powerful our planet's climate system truly is. Thanks for joining me on this incredible journey through deep time. Until next time, stay curious about the amazing world we call home.